This episode was recorded on site at Microsoft headquarters, where I was invited to see the launch of the world's first quantum processor powered by topological qubits, Majorana 1. I have to admit, I was super emotional being able to hold this chip in the palm of my hand. I've been waiting for this modality to become a reality for about a decade now, and the interview you're about to hear happened just a few feet away from a working Majorana 1 system. Find out all about this amazing breakthrough and how it will house 1 million qubits in this episode of the Post-Quantum World. I'm your host, Konstantinos Karagiannis. I lead quantum computing services at Protiviti, where we're helping companies prepare for the benefits and threats of this exploding field. I hope you'll join each episode as we explore the technology and business impacts of this post-quantum era. Our guest today is a technical fellow at Microsoft, Chetan Nayak. Welcome to the Post-Quantum World. And this is a weird episode because we're in person, and I just got through the most mentally exciting day I've had in a long time. For those,
thank you very much.
Yeah, this was amazing. I got to hold in my hands a topological, I guess, mini system. So I guess so Majorana 1, right?
Yeah.
So let's start with why that's amazing, right? That little thing I held in my hands. How many qubits will that one day represent?
Yeah. So I think what's amazing about it is that it's really a very different type of qubit architecture and different approach to quantum computing than the first generation of quantum machines. And something of that size, a single chip can one day hold 1 million qubits.
1 million.
1 million.
Yeah.
That's that potential end result is so different from what people are talking about now with multi-module machines where you're connecting hundreds or more cryostats, each holding some number of qubits, potentially requiring complex 3D integration. Our approach is to not do any of that, to sidestep all of that. In order to do that, we had to invent a new kind of qubit to be at the base of it, or at the core of it. And that's the topological core of our quantum processing unit. And hence the name Majorana 1, because it's based on Majorana 0 modes. And so, it's really a reimagining, a reinvention of quantum processors based on a new state of matter. Topoconductors, short for topological superconductors. And so we had to create a new state. What we've done is we've created a new state of matter. We've harnessed it into a new type of qubits. And those are the topological core of this kind of quantum processing unit, which we envision, if we look at our roadmap, we envision this all being on a single chip.
Yeah, and we've been talking topological for about 10 years now on the outsides of the industry, and you've been working on it for, I guess, twice as long as that. So I've been very excited for this, and I've seen it take different shape over the years, and of course there've been the ups and the downs, and more recently it's been all ups, and I've reported on it on this podcast a couple of times. So let's go through those steps. One of the biggest ones is creating an entirely new state of matter.
Yeah. So, we're all used to states of matter like solids, liquids, gases. We grow up learning about those. But there are other states of matter that are some more and some less subtle. There's superconductivity. That occurs in many materials. When you cool them down to very low temperatures, they're able to carry electrical currents without resistance. Okay? And so that's not the difference. That's not some physical or mechanical difference, like the difference between a solid and a liquid, but that's a difference that's more subtle that occurs with the electrons that are inside the solid. And they do what's called Cooper pairing. They form these pairs. Their wave functions become rigidly aligned with each other, these Cooper pairs. So it's quantum mechanical, and B, a really an effect that manifests itself in the electrical properties. What we realize is that there's another kind of superconductor, or what people realize, I should say, over the last 2 decades is that there are other kinds of superconductors with what are called topological superconductors, and those have this remarkable property that actually unlike a regular superconductor, which really cares whether it has an even or odd number of electrons, because in the odd case, one of them is unpaired and there's an energy penalty. You've got an unhappy electron somewhere. In a topological superconductor, actually, an odd number of electrons is just fine. It doesn't mind at all. There's no unpaired electron that you can find anywhere. It managed to hide that unpaired electron in the underlying ground state of the system. This, in turn, is an example of an even more general class of what are called topological phases of matter, in which the distinctions are these kinds of very subtle things that, very discrete, I should say, like even oddness is very discrete, these very kind of subtle distinctions that have to do with topology, which is the study of those properties of geometrical shapes that are invariant under, what are called smooth deformations. Okay, which is make small changes. You can turn, you take small changes to an untwisted band and it's still untwisted, right? You can stretch it, you can pull it. But if you take a Möbius band, which has one twist in it, there's no way by smooth deformations to get from the untwisted band to the Möbius band. Okay, to get from like a wedding ring to a Möbius band. And vice versa. So those kinds of topological distinctions, the wave functions, the quantum mechanical wave functions in these topological phases have those kinds of distinctions and the associated rigidity and the notion of how hard it is to like tear a band and then twist it and reglue it. That's a property of these states called the topological gap. It's an energy gap, an energy scale that tells you how robust and how stable these states of matter are. And so the larger you can make that, the more robust your topoconductor will be, the more robust your topological phase will be, and also the better your qubits will be. The more robust, the less error prone they'll be, but also they'll be smaller and you'll be able to operate them faster.
So is that gap what allows you to take an accurate measurement of the state of a qubit?
It is one of the important features, but it's not the only important feature. So in order to do an accurate measurement of the state of the qubit, you first have to figure out some way of this degree of freedom that's been hidden, the parity, which you're going to have millions of electrons in one of these topological topoconductor wires, topological superconducting wires. You need to be able to difference between millions and a million plus one, right? And so that's a very subtle difference. And so the way it's done is through something called interferometry, where in quantum mechanics there's this remarkable property that electrons actually, when can take multiple paths around a circuit, and they interfere in a similar way that light waves behind a double slit form an interference pattern on a wall. Purely quantum mechanical effect. And interferometers can enable you to measure topological information precisely because it involves something going around a loop. And so in order to do that, we take a topological superconductor and couple it to what's called a quantum dot. And that quantum dot, through that coupling, the quantum dot's properties get changed. It's actually sensitive to the quantum state. And our ability to connect the quantum dot to the qubit and the stability of the qubit rely on that topological gap. But it also relies, for instance, on the whole rest of the readout chain, because our ability to make an accurate measurement does depend on our ability to interpret the signal that comes out. So it is, I would say, fundamentally, the fundamental limits on device performance are ultimately the size of that topological gap. But there are some others that are also, so maybe one way of putting it is, you want as big a topological gap as possible, so the underlying qubit is as good as possible, and then you want to give away as little of that as possible in all of the subsequent steps you have to do to measure.
Okay, and the electronics to do this kind of measurement, when you mentioned before that a million qubits will fit on this tiny little, we're talking graham cracker, little chip.
Yeah, right.
How does that scale?
Yeah.
What happens there?
Great question. So there's two pieces of it. There's the control and there's a readout. Now the control is actually extremely simple, because almost all of the control that we do is you have a quantum dot, you couple it to the wire, you decouple it from the wire. While it's coupled to the wire, you're measuring. The quantum dot is measuring the state, and when it's decoupled, it's not. Okay. And the cool thing is we actually have different quantum dots that we can couple in different ways to our qubit. And some of them can couple to an individual wire. Some of them can couple to across wires, to two different wires within the same qubit. Some can couple between qubits. So we can actually do measurements of qubits natively in different bases. We can do a measurement in the X basis. We can do a measurement in the Z basis. We can also do 2-qubit measurements, ZZ or XX, for instance, in the same way. So we have the ability to do these measurements, and all we're doing is digitally turning on and off these measurements. So actually, the input, potential input bottleneck that you would have of trying to control 1 million qubits is substantially reduced. And in fact, we send relatively little information down to the fridge, and that information is then by a cryogenic CMOS controller, a classical controller, is then sent out to all the qubits. So another way of saying it is there's a fundamental challenge in controlling qubits at scale, which is that there's nothing like Grenz's rule, which says that you may have 1 billion transistors on a chip, but only a few thousand control lines. Okay, because the signals can fan out. There isn't on the quantum processor itself or on the quantum chip, there isn't that kind of fan out. Every single qubit has to have classical control lines. So the way that we get around that is to have something in the cold, very close to the qubit, that effectively does that fan out for us, that receives digital messages and then sends out the voltage pulses. So it's the fact that these pulses have carried very little information with them. They are just, you turn on a measurement, you turn off a measurement. They're very digital, that enables us to avoid that input bottleneck. And that, in a sense, that is very closely related to topology, because topology is actually a very discrete thing. All of the continuous deformations you do to shapes, topology doesn't care about that. It's really focused on the kind of the discrete information that you have. And that's true also of the electronic wave functions and of the device configuration, that discrete aspect to it. There's also a readout side. Okay, so you're turning on and off the couplings to the quantum dots. You then are going to also read out what was the effect on the quantum dot. That readout side is actually much more analog, because you are measuring a phase shift, but we then discretize that actually up at room temperature, because we can substantially multiplex those microwave signals that are coming back out, and we need to just be able to tell, was it a 0 or 1, the measurement, the result that you got.
Which could be handled in that other end of the bandwidth.
Exactly. And doesn't involve any complicated pulse shaping or timing or anything like that.
Okay. So in theory, maybe even the readout is less prone to error.
Yeah.
Yeah. So the chip I held in my hands contains a grid of 4 by 2 qubits?
Correct. Yeah.
Okay.
Yeah.
So that's what we have right now.
Yep.
And that form factor will not change when we go to 1 million.
Right. So if you look at the chip, if you look at the processor, the underlying qubits are smaller than 10 micron by 10 micron. And that's actually a pretty nice Goldilocks regime. If the qubits were smaller than that, actually it'd be almost impossible to get the wiring in. Okay. On the other hand, if they're too big and you need 1 million, you're going to be on many chips, potentially many modules, maybe even an entire warehouse is what some of the, some of the roadmaps that I've seen. But if you got something that's 10 microns by 10 microns, then, 1 million qubits is 1,000 by 1,000. And even though you will need some space for the wiring and control structures and so on, it's still putting you in a few centimeters by a few centimeters. So those are still, that roughly that form factor that you saw.
That one little thing hanging off of a fridge. That's it.
Yeah.
And it's all there. Incredible. So that prevents your need for any kind of interconnect or anything like that for a long time.
Yeah. So we didn't want to both solve the problem of quantum computing and solve the problem of quantum networking in order to make something useful, right? So, there may be certain situations in which it's advantageous to have a quantum network, and it's advantageous to do some kind of distributed computing, and you don't want to shut the door on that. But we also don't want to be, and I believe we're not in a case in which we are entirely dependent on quantum networking in order to make a system that can solve useful problems.
Okay. So this year we're expecting 50 logical qubits from Microsoft's work with Atom, right? And all the qubit virtualization, everything that we covered on this show.
Yeah.
So those learnings, they're going to be applied here, I'd imagine?
Yeah, absolutely. We've been learning a lot about quantum error correcting codes, not just in the asymptotic limit, not just for some idealized error models, but for, for specific system sizes and for specific hardware, which, all these hardware modalities have different, some things are harder, some things are easier. And the types of errors that occur are very dependent on the hardware. We have been learning how to tailor the code and actually co-design the error correcting codes with the hardware. All those learnings in the same discipline, we're learning from that. We're also applying to our own hardware.
Okay. So this first chip, I see some here actually running and everything. What's the plan for that being live in some form on the cloud? Like, what does the first Majorana access look like?
Yeah.
Is it something this year, even on a simple test base?
The answer is I don't think we know for sure yet. I don't know exactly what there's a market for. We know we have a much better idea of what the end state is, right? Which is that we want utility scale quantum computers, so fault tolerant quantum computers that are large enough to solve otherwise unsolvable materials and chemistry problems. Those are problems that, we are a cloud computing business, right? That is Microsoft's core business, and we expect that to be an integral part of Azure. In between now and then, it's a little unclear exactly what there's a demand for. I think that there definitely are people who are more of a research bent who want to be able to play around with systems that are available that exist right now, to learn with them, maybe to peek under what's under the hood and understand how these things work at a physical level. But there's also people who would rather say, you know what, I want to be many abstraction layers away from all of that stuff, right? I just want to be up here and just write quantum software and, not worry about what's happening down at that lower level. For those people, I think they are going to be much more interested in that end state. So I think it depends. We don't really have a plan right now to release into the wild any of these smaller systems until, prior to fault tolerance utility scale. But, that could certainly change depending on what there's demand for.
Yeah, I was thinking along lines of research, like people like to see papers and what they ran on. It's reasonable to expect that any papers that come out will be coming out from you guys on stuff done here. Yeah. And not just folks tapping in.
Right.
Do you have any guesses at what kind of ratios of qubits would produce what kind of logical yield?
Yeah, I mean, we have pretty good ideas of, what kinds of codes, what distance surface code, for instance, you're going to want at the scale of useful fault tolerance and, or ultimately utility scale. I think, the interesting ratio, when we get out to utility scale is going to be in the hundreds, just to be clear, of physical qubits per logical qubit.
Okay.
Exact numbers depend on details, but that's where I think these things, really start to become, my way of thinking about it is that point of where you really would say I have a useful fault tolerant computer is your logical error rates are less than 10 to the minus sixth. So one error every million or so operations. And, logical qubits in the 5 to 20 count, So that's where you start to get interesting. Of course, 50 logical qubits, 100 logical qubits is really interesting, but that's the point at which things become, I'd say, you have definitely crossed the threshold to where you can say from here on we're scaling up.
Yeah, and Microsoft has some pretty rigid definitions of logical. They're not playing fast and loose, right?
Right.
These are very usable qubits.
That's right. So it's really important not only that you be able to detect and correct errors, but that you need to be able to do computations with them. So it's not just a quantum memory; it's actually logical qubits that you can operate on.
Yeah. And I know my listeners could never feel this personally, but having dreamt of topological qubits for so long and to be here today and see it with my own eyes was kind of insane. It was a really moving moment. Yeah.
Awesome. Thank you. Yeah, believe me, I feel the same way. So,
and I'm still here. I know you and I have talked before and we joked about Majorana, and after he discovered the Majorana fermion, he disappeared about a year later. So, I'm still here. So look at that.
Exactly, right? Yeah, we haven't suffered the same fate.
Yeah, we live to talk about
That's
it.
reassuring, yeah.
So let's talk about use cases for a second. I think it's interesting that Microsoft's going so hard and heavy into chemistry.
Yeah.
You want to talk a little bit about that?
Yeah. I think from the earliest days of quantum computing, and if you think even about Feynman's earliest papers, right?
Simulator,
he said, what his motivation was, it's really hard to simulate quantum systems because Hilbert space is huge. So if you go, if you want to do a 100 site solid, let's say, or a spin system with 100 sites, you need this huge Hilbert space, which is 2 to the 100 dimensional. And so that you're never going to be able to do on a classical computer. You're not going to be able, and once you get into thousands, let's say, there aren't that many atoms in the known universe.
Yeah.
So that's definitely not something you do with the classical computer, except for the interesting case in which we discover something really unusual about quantum mechanics that tells us that there's some classical theory hiding behind it, right?
Yeah, that it's not the lowest level of reality.
It's not the lowest level of reality, and there's something actually even more fundamental. But let's assume that's not the case, right? Every indication we have is that quantum mechanics is the right theory. And so we're not going to be able to simulate those things, on a classical computer. And so what a quantum computer is kind of ideal for is those types of problems. And if you look, you develop processors that are ideal for certain things. Like GPUs are ultimately they're doing matrix multiplication, right? GPUs and TPUs, you're trying to optimize for something that's good at matrix multiplication. CPUs are very general purpose, but they are, they do things like, arithmetic logic and certain kinds of operations. They are,
they're Turing tape machines, basically.
Yeah. But, they take some set of instructions, they figure out some dependencies, and then they break them into chunks and execute on them, right? And they do that in a fairly flexible way, based on some ideas of what kinds of instructions they're getting. So what is it that a QP or a quantum processing unit is really, what is it tailor-made for? Well, it's tailor-made for doing operations in a Hilbert space, right? Or simulating operations in a Hilbert space. And the great thing is that actually isn't, it seems like, but it's actually not some weird niche application, It's actually, just as GPUs turned out, it's not just for gamers, right? It's not just for really good graphics for
AI,
gamers.
mining Bitcoin,
AI, lots of things, right? Well, quantum computers, simulating quantum systems, well, that is the language of nature, right? And so there's, many things, materials, chemistry that are very difficult to otherwise simulate. Actually, my career in physics started thinking about superconductors, high temperature superconductors. Those were discovered in the late 80s. And, they were really a big revolution. People knew about, for over 100 years about superconductivity. I think mercury was the first superconductor discovered by Kamerlingh Onnes, in Leiden back in the early part of the 20th century. People knew about aluminum, lead, lots of other things. It was really a revolution in the late 80s when these other materials like yttrium, barium, copper oxide, lanthanum, strontium, copper oxide, these materials were discovered with these very high, superconducting transition temperatures, over 100 Kelvin. So, above the liquid nitrogen temperature. So you didn't need liquid helium. You could cool them down with liquid nitrogen. And at the time, people, there's a lot of excitement that we might have room temperatures. The temperatures are going up. Maybe we'll even have room temperature superconductors.
We just tasted that recently when literally everyone in the world was trying to recreate it.
But the honest answer is we don't know exactly why those materials are superconducting even at 100 Kelvin. And we don't know what the fundamental limits are. Could there be, room temperature superconducting materials, or even just a little bit higher temperature? Those are fundamentally systems in which, out of pretty simple constituents, which is just electrons and ions and the mutual interactions, these really complex behaviors emerge out of them. And they emerge out of the quantum mechanical interactions between these collections of electrons and ions, which have pretty simple underlying laws and equations, and yet a very complex behavior emerges out of them. And it's fundamentally quantum mechanical. And we really can't simulate those systems, on a classical computer. And that's not just true of superconductivity. It's true of magnetism. It's true of, other kinds of really interesting and fundamental materials properties. And, early in my career, I was looking at those kinds of materials and trying to understand them, trying to come up with theories of them, looking at the data, trying out different approximations that give us some kind of like classical insights into how these materials work. But, really the way to solve these kinds of problems, to understand the materials, is to use a quantum computer. And that's kind of the direct, approach to understanding these. And, I think these kinds of materials are super important for the future of technology. There are lots of things that we could look at technologically that we could do with humanity that are, like, the laws of physics don't preclude them. It's just that they're really hard to do. And in many cases, it's because the properties of the materials that we have just aren't, they could be, but they aren't good enough to do those things. And so if we have a deeper and better understanding and richer understanding of materials and the potential properties and the ability to design materials, that really could open up a whole, new set of possibilities. And now I'm thinking about the material context, but that's really also true in chemistry. So right now, a lot of discovery of things like catalysts or drugs. There's a huge trial and error component to it, and simulations, because many of these things are have an underlying quantum mechanical basis and are molecules that are a bit too complex to solve. Our simulations are of limited use in many cases, and having quantum computers would really change the way we operate in a lot of those things. Really narrow down the possibilities from, a large search space to a much smaller set that's most promising, which you would then in the lab approach.
Yeah, and a lot of this is working in tandem with AI. I know that's been a big thing.
Absolutely, yeah.
The Quantinium announcement and other approaches.
Yeah, so I think all these things are part of the puzzle together. Quantum computer is good, or quantum processor is good for specific things. What people maybe don't always appreciate is this isn't just, quantum computer or a quantum processing unit is not just a 10x faster version of a classical, or 100x faster, or a million x faster. It's not just a faster. It's fundamentally different. It really, I know it's overused to say it's apples and oranges, but many things that a classical computer does now, a quantum computer will be terrible at. It will be extremely slow and bad. And then there are things that a classical computer today could never do, right? That a quantum computer can do when it gets that scale would be relatively easy for a quantum computer to do. So, when you look at a quantum computer versus a classical computer, there is a little bit of the hard is easy and the easy is hard, right? There's a lot of things that are easy for today's classical computers that are really hard for a quantum computer. A lot of things that are super hard for a classical computer would be easier for a quantum computer. So they really are, in a sense, very complementary. So you're going to need both. And with any given workload, you will be giving some parts of that problem to the quantum processor, some parts to the classical processor.
So it's feasible so I held Majorana 1. It's feasible that Majorana 12 will find a way to improve the materials to make Majorana 13 or something. It's possible.
Absolutely. You're not the first person to come up with that wisecrack. I'll tell you that. That's something that we've said. Even like decades ago, I remember joking about that. If we just had a quantum computer, we'd know how to build a better quantum computer. So.
Yeah, absolutely. Yeah. But it's amazing that we're even here. So, like I hinted at before, I know that you've been at this like 19 years. Right?
I've been at Microsoft for 19 years, all of it within one version of the quantum program or another.
Wow. Yeah. So how does this feel for you? This is quite a moment.
It's really exciting. It's really, I can tell you the moment when I saw some of the first data from some of these devices, that we showed you today and earlier generations, it definitely was spine tingling. There was that sense that, okay, here are these things, these Majorana zero modes, these topological superconductors, these things that are, the math is right, the math works, but are they really going to exist in the real world? That's a higher hurdle. And when we first started seeing some of the data that looked exactly like, what the theory predicts, that was pretty very special moment.
Yeah, I bet. I got to see some of the art that's going to be, I guess, in the Nature. Well, if you're listening to this, the Nature article is live online. And of course, there's a Microsoft blog and everything that'll be live. So all that'll be linked in the show notes because I strongly encourage everyone to take a look to fully grasp this. But thanks for making this a reality. It's just incredible. I cannot believe I'm here and I saw what I saw.
Thank you very much. I'm glad you came. And it was great spending time with you and discussing this. Appreciate it.
Thanks. Now it's time for Coherence, the Quantum Executive Summary, where I take a moment to highlight some of the business impacts we discussed today, in case things got too nerdy at times. Let's recap. If you're listening as this episode goes live, Nature just released a paper validating how Microsoft created a new state of matter to get topological quantum computing to work. The new material stack of indium arsenide and aluminum, built literally one atom at a time, is a topoconductor, or topological superconductor. Majorana zero modes, or MZMs, are created on the topoconductor and can store quantum information based on whether an odd or even number of electrons are present. To take a measurement, a digital switch couples the ends of the nanowire to a quantum dot. Microwaves then reflect off the dot to tell the odd or even state very reliably. The resulting qubits, called tetrons, due to their four-ended H-like shape, are less prone to error, which should lead to better error-correcting ratios of physical tetrons to logical qubits in the future. Think hundreds to one for rock-solid logical qubits with 1 in a million or fewer errors. The Majorana 1 chip currently holds a 4x2 array of tetrons, but as each qubit is only 10 microns wide, it can hold 1 million qubits in a couple of centimeters one day, without changing form factor of the module. As I said, I held this QPU in my hand, so the miniaturization is amazing. There's a control chip on board to prevent the need for excessive wiring running down the fridge and into the board. Microsoft has already announced DARPA advanced them to the next stage of the US2QC program for creating a fault-tolerant system. Microsoft is expected to build out fault tolerance with 1 million qubits in this architecture in what they call years, not decades. Microsoft believes the first killer application for such a machine will be in chemistry and other simulations of the quantum universe. This is very much in line with the simulation work Feynman envisaged back in 1981 when he came up with the idea of a quantum simulator, and will be made possible by an older, fascinating discovery by Ettore and Majorana in 1937. That does it for this episode. Thanks to Chetan Nayak for joining to discuss Microsoft's first topological QPU, the Majorana 1. And thanks for listening. If you enjoyed the show, please subscribe to Protivity's The Post-Quantum World and maybe leave a review to help others find us. Be sure to follow me on all socials at Constant Hacker. That's Constant with a K, Hacker. You'll find links there to what we're doing in quantum computing services at Protivity. You can also DM me questions or suggestions for what you'd like to hear on the show. For more information on our quantum services, check out Protivity.com or follow Protivity Tech on X and LinkedIn. Until next time, be kind and stay quantum curious.